thank the organizers for having us today and giving us the Startup of the Year award. In the next 10 minutes, I'll review some of the challenges in building a useful quantum computer and tell you the cat qubit story of Alice and Bob and how we're aiming at achieving this. So I think many of us today are in this room because we believe that quantum computers will be the next technological revolution and will allow to solve a lot of problems much faster than what we think is possible today. More precisely, the reason we're here is because we believe that there are some quantum algorithms which can solve problems exponentially faster than classical counterpart. But how fast is exponential exactly? Let's look at an example, for instance, the problem of factoring integers into their prime factors. If you were to use the supercomputer Frontier today, which is one of the most powerful, then it could factor an integer of 500 bits in about 1 millisecond, which is the time it takes for a hummingbird to flap its wings. If you double the size of that integer, it will already take on the order of 3 months for the computer to solve the same problem. And if you double again the size of the integer to 2048 bits, then it would take about 400 times the age of the universe to compute that problem. This is because solving such a problem on a classical computer is exponentially hard. On the other hand, for a quantum computer, there exists an algorithm, Shor's algorithms, which can do the same in polynomial time, which means that it could factor an integer of size 2000 bits in about a few days or a week. And it is because we believe that there are such speedups that can also apply to other industries like life sciences or chemicals or energy that we want to build a quantum computer. So how does it work today? Why is a quantum computer so fast? You know that for a classical computer operates on classical bits, which can take two values, 0 or 1, which can be represented as an arrow pointing up or down. For a quantum computer, a quantum bit can rather be represented on a sphere called the Bloch sphere, and any point at the surface of the sphere is a possible quantum state, thanks to quantum superposition. If the quantum state lies on the equator, then the qubit has an equal probability to be in 0 or 1, and the position on the equator rather tells you what is the sign of the position. If it's plus or minus, then you have a well-defined quantum state with a real phase. If it's elsewhere on the equator, then you have a complex phase between the two. Now, the issue in building a large-scale quantum computer is that qubits are not perfect. Because they interact with their environment, you can have some errors. For instance, you can have a bit flip, which flips the value 0 to 1, or you can have a phase flips, which flips the value of the bit from minus to plus. When you have all of those errors at the same time, then we say that the qubit decoheres, and very quickly the state of the qubit is the quantum information encoded into the qubit is destroyed. For many physical systems that we use today, this happens on a time scale of a few hundred microseconds to a few milliseconds, which is in contradiction with the fact that you want to perform a computation which should take hours or days or even weeks to complete. So there is here a paradox in building a quantum computer. On the one hand, you want to build very good qubits, so they should be completely isolated from their environment. The way to build qubits that have a long lifetime is to put them into a black box where nothing can interact with the system. But on the other hand, we're trying to build a computer, which means you should be able to initialize the state of the system, perform computation on the system, and then read out the result of the computation. But if you can do that, then so does the environment. And so there is a kind of contradiction in building something that's completely isolated, but that only you can control. Today, the best way, the best technological way to do this is the so-called FTQC paradigm for fault-tolerant quantum computing. It works as follows. The idea is that rather than using a single qubit to encode a bit of quantum information, you will use many physical qubits to encode the same bit of quantum information. Then you can check very often whether the different qubits agree with each other, and if one of them disagrees with the others, then you will interpret that as a quantum error has happened on this qubit, and so I should correct it. The fundamental hypothesis for this to work is that the errors on qubits should be independent. If all of the qubits have an error at the same time, then they will still agree with each other, but you will still have an error. And another thing that's important is that the more qubit you put into this set, then the better the encoded information becomes. Now, how many qubits should we put exactly into this large array of qubits? If we take the typical errors that we have with today's technology, and you look at the typical time of the computations we want to run, let's say a few weeks, then the order of magnitude that you find is that you actually need to put 1,000 physical qubits into a single so-called logical qubit for it to be good enough so that you can run a long computation of interest. Now, the problem with that is that it means that for building a single logical qubit, you already need 1,000 physical qubits. Typically, the scale at which you operate such a system is with a full cryogenic system and a full racks of control electronics, already costing about $10 million and consuming about 50 kilowatt. This actually is the scale of where we are today. For instance, the largest chip built by IBM and operated by IBM was on the order of 1,000 physical qubits. And recall that this is only to build a single logical qubit that lives long enough to run a computation. Now, if you want to have a quantum advantage in the sense that building a machine that actually makes some money, then you should use at least on the order of a few hundred logical qubits, which means you need 100 cryostat, and now the price of the system would be closer to $1 billion and to a megawatt of energy consumption. To run, this is, by the way, the order of magnitude that current data centers operate on. If you want now to operate the largest, to run the longest algorithms that we can envision today, then you'd need rather on the order of a few thousand to few tens of thousands of logical qubits. And so, this is of course not so reasonable, but the scale would be like a 200-floor story building costing a few $1 billion and operating, requiring a few hundred megawatt of energy. So I think this is a bit overwhelming. So we're thinking the founders of Alice and Bob, and we thought, this is actually the roadmap of IBM and Google, for instance, but surely there's got to be an easier way. So now I'll tell you the story of the cat qubit and how we envision reducing those numbers. Cat qubits are built using microwave photons. It's actually the same as other technologies like Google and IBM, but in their case, the qubit is built on whether there is a photon or no photon. In the case of Alice and Bob, we rather take advantage of the fact that a photon can also be seen as a microwave, as an electromagnetic wave, which has a frequency and amplitude, and we rather encode the information in a coherent state where we have many photons with the same amplitude and same phase. This is called a coherent state of light, which is also the state of the laser light. Now we trap such light into a superconducting cavity, which is just a piece of superconducting metal like niobium or tantalum on a chip, and then the cavity starts oscillating at the same frequency than the photons. We can represent this to understand why this is interesting. Let's look at the Wigner function, where this oscillation can be represented as a globe. The amplitude is really of the electromagnetic wave is really how far the globe is from the origin. It's proportional to the average photon number that we put into the cat state. Because we want to encode a quantum bit of information, we need two states. So we use two coherent states with the same amplitude but opposite phase. When we put them in superposition, it's somewhat a superposition of two macroscopic objects, almost classical objects. So by analogy with the thought experiment of Schrödinger, we call that a Schrödinger cat qubit. The interest is that now, if you think of bit flips on such a system in terms of that representation, then it means that the blob 0 has to jump to 1. But because the amplitude, because the distance of those two states is set by the average photon number, by increasing the photon number we put into the cavity, we can make that jump more and more difficult to happen. More precisely, this is experimental data that we've obtained with a chip that we have put on the cloud, so we can log it into the internet and reproduce that experiment. And here you see the lifetime in log scale of the bit flip as a function of photon number. Lifetime in log scale means the average time it takes for a coherent state to jump to the other side, which is what we do not want to have. And as you can see, as we increase the photon number in the cavity, we very fast reach a regime where this happens only every once in a few minutes, where for other technologies this would happen many orders of magnitude much faster on the scale of the few milliseconds. So because of that, in a nutshell, we don't really have to correct for bit flips anymore because they are so rare, so we can only build a single line of cats when competitors would require a full array of qubits. So this is a picture of the system that we're building right now that will demonstrate this. in a nutshell, how does it affect the size of the quantum computer? We can then have a more elaborate version of such codes and use LDPC codes, which are used in a technology like the 5G or the Wi-Fi, which is so hard to adapt to the quantum setting. But here, because we have cat qubits, we can adapt it and find a 200-fold reduction of the final size of the computer. So in a nutshell, this is how we, at Alice and Bob, we envision building a useful quantum computer, and we think it will become practical much sooner than envisioned, because instead of needing that huge building operating millions of physical qubits, we think it's reasonable to run a much smaller scale, actually on the scale of a data center, because we use cats. Thank you for your attention, and if you want to read, that was a major oversimplification. If you're interested, we have a very good roadmap and white paper on our website that this QR code will lead you to. Thanks.